Section 3.4, Implicit Differentiation. In this section, we will use implicit differentiation to find the derivative of a function defined implicitly, and we will also solve applications involving implicit differentiation. So up until this point in time in this class, we've been working with equations that are written explicitly, meaning the y is on one side of the equation and all the other x's or t's or whatever other variable we're using are on the other side of the equation. So for example, y equal to x squared minus 3x plus 4, or for instance, p of t equals to 7t plus 3 divided by 4t. These are what we call explicit equations because the dependent variable y, for instance, is written explicitly in terms of all the independent variable x's. Now, some equations are not written like that. For example, the equation x squared plus 4y squared equal to 12 is not written explicitly. We don't have what y is. We need to solve for y, and sometimes it's difficult to solve for y, or maybe even impossible to isolate the y variable. So for example, if I look at the equation 3x squared minus 7x cubed y4 plus 2y squared equal to 9, this equation has the letters y and x on the same side, and if you try to solve for the letter y, it will be very, very difficult or even impossible to solve for y. So what if we want the derivative with respect to x of the variable y? What do we have to do? What can we do? Can we even find the derivative? And the answer is yes. We will need a process called implicit differentiation to find the derivative when the equation is not written explicitly. So in other terms, if your equation has the letters x and y all together on the same side, and you don't want to solve for y, and you still want the derivative, there's a new process called implicit differentiation that can help you out. And this process really relies on the previous two rules that we learned in the previous sections, the basic differentiation rules, along with the product, quotient, and the chain rules. So how would it work? How does it work? Well, let's take a look at the example number 1 where it says find the derivatives, and we've got different things. So in the first part, we have d over dx with x cubed. So in this problem, the important thing to remember is that we're differentiating with respect to the letter x. That's what's written on the denominator, the dx. And what are we differentiating? We're differentiating the quantity x cubed. So the letter on the denominator, dx, matches the variable that we're differentiating. So these are the same variable. So what we do is we find the derivative like we've been always doing it in this class. So we just drop the power down and we subtract 1 from the existing power so that we can have the 3x squared, and that's it. We call it a day. That's the end of the problem. So if the variable that we're differentiating with respect to is the same as the variable that we have in the problem, we don't need to do anything new. We just differentiate as usual and we move on. Now in part 2, we have the derivative with respect to x of the letter y cubed, or the variable y cubed. So in this problem, the denominator has dx, but the variable that we're differentiating, or the expression that we're differentiating, has the letter y. So these are not the same. So what do you do in these problems? Well, first, you differentiate as if it was the letter x. So you just say, okay, derivative of y cubed is 3y squared, because, 3 minus 1 is going to be 2. So we'll just write down 3y squared. But because the variable that we're differentiating, which is the letter y cubed, is not the same as the variable on the denominator, which is the dx, we will add an extra dy over dx. So this represents basically what we did in the chain rule as the derivative of the inside. So we're thinking of the letter y as being a function that has a lot of x's in it. So this letter y that we're differentiating may have been something like x plus 3, or maybe, I don't know, 2x plus 5. So it's some quantity that has a lot of x's. And when you differentiate that quantity using the general power rule, you need to find the derivative of the inside, but we don't know the inside, so we just write a little reminder on the side saying we still want dy over dx. And in that case, this will be the final answer. So if the variables don't match, just remember you need to add the derivative of the inside, dy over dx, to the side. So let's look at part 3, where we have a mixture. So we're differentiating with respect to x, the quantity x squared y cubed. So in this problem, we actually have a product of x squared y cubed, And the variable on the denominator, we have the x basically, so the variable is x, but we're differentiating a mix of x squared and y cubed. So this is the mix of variables, and it's sometimes the same, sometimes it's not the same as the variable on the denominator. So what do we do in this case? Well, first of all, because of the product that we have in the middle, we will be using the product rule. So because of this multiplication, you'll have to use the product rule. And the product rule says write down f and write down g, and you'll also need to write down f prime and g prime. And you have to multiply some corners, adding along the way. Now, our f is everything that comes before the multiplication sign. So f in this problem will be x squared. And y cube is the g variable. That's the second thing that is in the product, the second term. So that's going to be my g. And so now mentally, I'm going to pretend like I'm differentiating x squared and y cubed, and I'm going to write it on the side over here. But what am I differentiating with respect to? I have to remember for this problem, I'm always differentiating with respect to x. So what's the derivative of x squared with respect to x? Well, the variables match there, so derivative of x squared is just going to be 2x, and that's it. So we're done with the f. What about the g? So I want the derivative of y cubed, but I'm differentiating with respect to the letter x. That's what the problem told me to do. Well, the derivative of y cubed is going to be 3y squared, but the letter y does not match the letter on the denominator that I'm differentiating with respect to. So therefore, I'm going to have to add the dy over dx, the derivative of the inside. Now my product rule basically tells me to multiply some corners with each other. So multiply those two corners and we get 2xy cubed. The product rule tells me to add at some point in time. So I'm going to go ahead and add. And what am I adding? The product of the other two corners. So the other two corners are x squared multiplied by 3y squared and dy over dx. And if you like, you can put the 3 in front of the x squared. It's not wrong. It's better actually to do that. And that is how we find the derivative of this expression. So it sounds complicated, but remember we're thinking of it as a product rule because the y is a function of x. That's what we're assuming. And because the y is a function of x, it has some inside, but we don't know what the inside is. So we just write a little reminder saying we need the derivative of the inside. So tell me the y, and I'll tell you the derivative of the inside, but we will write it over here. So this dy over dx acts like a placeholder for the derivative of the inside. So if we knew what the inside was, we would write it here. But since we don't know what the derivative of the inside is, we just write the reminder saying we will need it on the side. So that's how you differentiate a problem when you have a mixture of x and y, and that's very common. We're going to see a lot of problems in this section where we have a mixture of the letters x and y. So remember, if you've got like a product in the middle, you need to use the product rule. But if I had something like x squared over y cubed and I wanted the derivative with respect to x, then in that case, I would need the quotient rule for this type of problem. Okay, so that's the end of the introduction part of the section. So let's go ahead and take a look at how this process is done when you have an actual equation. So if I have an equation like x squared minus 4y squared equal to 2, and I want the derivative of y with respect to x, how can I go about finding it? And the answer is we will need to use implicit differentiation, and there are some steps that we described in this little box. I recommend that you try to memorize them or at least write them down on a piece of paper or just watch the next parts of this video to see how we do this process. So in my example, number 2, I am given x squared minus 4y squared equals to 2. And notice what they want from me. They want dy over dx. So they want the derivative of the letter y with respect to x. Now, one thing I could do is take this equation that I have and isolate the letter y. That involves moving some stuff around, dividing by some numbers, and then square rooting the whole equation. It's going to take a lot of time to do that. But instead, now we will use the implicit differentiation process to get the derivative. And you'll see it's not very, very complicated. So step 1 in the process is to announce to the world your intentions. Like basically tell the universe, tell the world, tell the person reading this what you want to do. And what you want to do is you want to find some derivatives. So that's what I'm writing over here. ddx, and then ddx. Whatever you do on one side, you do on the other side. So this is the step number one. And why am I writing ddx? Because the problem that I was given told me to differentiate with respect to x. That's why I'm putting ddx and ddx. Now, the y that I need to have on the numerator will eventually show up when I differentiate the term for y squared. That's going to create the dy over dx. So that's why we don't put the y over here and the y over here. We just put d over dx. This is like an announcement saying to whoever's reading this that I'm planning to take the derivative of both sides. And because I'm doing it to both sides, it's perfectly acceptable. It's perfectly fine. And now let's actually do it. So what's the derivative of x squared with respect to x? So in that case, the variables are matching. So derivative of x squared, we drop the power and we subtract 2 minus 1, which is going to be 1. You know what? We're not going to even write it, so just 2x. Now moving on to the next term, we have a negative, so we'll put it there. We have a 4, so we're just going to write it down, and now we have dy squared. What's the derivative of y squared with respect to x? Well, normally the derivative of the letter would be 2y to the power of 1, and I'm not going to write the 1. But the letter I'm differentiating is y squared, and I'm differentiating with respect to x, so they don't match, so that's why I'm going to write the dy over dx. And it's equal to the derivative of 2. So in this case, the number all by itself gets differentiated and becomes 0. So that is step number 1 of the process. Now, step number 2 in this process is to isolate the term that contains the dy over dx. This is the dy over dx. We want to put the term that contains it all alone on one side of the equation, and everything else has to go away and go to the other side. So find out where your dy over dx is and try to isolate the term that contains it, meaning put it all alone. So that means, first of all, that the 2x has to go from here to the other side. And technically, right now it's positive, so when I move it, it's going to become negative. So I'll end up with 4 times 2y times the dy over dx equal to, and then we'll have the negative 2x moving across. And by the way, the negative 4 times 2y is really negative 8y. So let's just simplify that and write it as negative 8y dy over dx equals to negative 2x. So this step is the isolate step, meaning figure out where your dy over dx is. Whatever term it's in, make sure that that term is all alone on one side of the equation. That means move everything else to the opposite side. Step 3 in this process will be to now try to factor out the dy over dx. If there's multiple terms, if there's multiple boxes that have dy over dx, make sure you take away the dy over dx from all of them. So I'm going to, in this case, there's nothing to do really, but I'll just put a little reminder here that I'm taking out the dy over dx from all the terms. And if I have multiple terms, I would have like 8y plus or minus some other numbers, but in this case, I don't. So this is the end, and we're almost done. Step number 4 is to now put the dy over dx all alone. So get rid of everything that's next to it. So in this problem, the stuff next to the dy over dx is negative 8y. I need to make it disappear. And keep in mind, it's being multiplied by the dy over dx. So to make it disappear, we just do the opposite of multiplication, which is division. So we divide both sides by the negative 8y. So the final answer is that the dy over dx, the derivative that we're looking for, is just x over 4y. And how am I getting this? I'm getting this because I'm dividing by 2, actually by negative 2, the numerator and the denominator. And so my final answer is that the derivative of y with respect to x is x divided by 4y. So that's our first example of how to do implicit differentiation, and I hope that made sense because we're going to use it multiple times, and this is a really useful strategy when your equation contains both x and y on the same side and you don't want to spend time isolating the y first, then differentiating after. It's a whole lot better to just do implicit differentiation. So in example 3, we're going to try to relate what this dy over dx does to the graph of a relation. So let's begin by looking at the graph of x squared plus y squared equal to 25. So x squared plus y squared equal to 25. Maybe you remember from algebra that this is the equation of a circle. And in general, the equation of a circle is of the form x minus h squared plus y minus k squared equal to r squared. So anytime I see that my x is squared and my y is squared, and they both have the same number in front of them, I'm thinking to myself, this is probably a circle. All I have to do is identify the center of the circle, meaning the point in the middle, and the center is hk always. So I look at the number next to x, I look at the number next to y. There are no numbers in this problem, so for me the center is 0, 0, since there's nothing next to x and next to y. And the radius of the circle, meaning the distance from the center to the edge of the circle, is the square root of this number. So I know that r squared is 25, so r itself is going to be the square root of 25, which is just really 5. So my center is 0, 0, and I have to walk 5 in all the directions. So this is the tip of the circle, this is the other tip of the circle, this is the other tip of the circle, and so on and so forth. So that's where my circle should kind of start and end. And if I draw the circle, it should look something like this. So this is what the equation x squared plus y squared equal to 25 would look like when it's graphed. Now, our TI calculator cannot graph circles very efficiently and very quickly. So this is why I spent a little bit of time talking about all this stuff that is kind of a reminder that you may have seen it in an algebra class before. And now that we have the graph, what do we need to do with it? So in part 2, it says find the dy over dx and then use it to determine the equations of the lines tangent to the curve at 3, 4 and negative 3, 4. Draw those tangent lines on your curve. So let's break it down step by step. First, there are some interesting points that they're talking about. The points are 3, 4. This is one of them. So this is the point 3, 4. And there's another point called the negative 3, 4. So the x is negative 3 and the y is 4. So this is the other point that they're talking about. Now, at these locations, there are some tangent lines, and they want me to draw those tangent lines, so we'll do that in a second. But that's what the tangent lines are going to look like. They're basically just random lines that touch the circle exactly at one location, where the point is 3, 4, or the point is negative 3, 4. So what do they want me to do? They want me to find dy over dx, first of all, meaning the derivative. And then they want me to use the derivative to find the equation of these lines that I just described over here. So this guy has an equation, y equal to some stuff. This guy has an equation, y equal to some stuff. What is the stuff that should be there, right? What's the equation of the line that describes the line over here, tangent to the circle? And what's the equation of this line that is tangent to the circle at the other location? Now remember, to find the equation of any line, you need to know the slope and the point on the line. So that's the purpose of finding dy over dx first. This is the derivative. It's still going to give you the slope of the line. So anyway, let's see how this is done. So first, the given equation is x squared plus y squared equals to 25. So this is what's given to me. And in step number 1, I'm going to tell the universe, tell the world, tell whoever's reading this, that I'm planning to do some derivatives. So I write d over dx, and whatever you do on the left, you're going to do on the right as well. So this is just like an announcement saying, I am planning to do some derivatives. And once you write the announcements, you start differentiating. Derivative of x squared with respect to x. The letters there are the same, so we just find the derivative as usual. We write 2x. Now, I need the derivative of y squared with respect to x. Well, the letters there are not the same, so I write 2y, and then I need to add the extra little new thing, which is the dy over dx, the derivative of the inside, because it's technically a chain rule that's happening over here on the y. Now it's all equal to, because the problem used to have an equal sign, the derivative of 25. Well, this is just a constant. It doesn't have any variables, so the derivative of constants is always 0, and that's it. So that was step number 1. Now step number 2 is to isolate the term that has the dy over dx, meaning get this term all by itself on one side of the equation. So what does that mean? That means I need to make this 2x disappear. And how can I make it disappear? I just need to move it across to the other side. And the way I do that is by subtracting it, because technically it's being added currently. So I need to subtract 2x from both sides, and that will give me the 2y dy over dx equals negative 2x. Step number 3 is to factor the dy over dx from all the terms that have the dy over dx. Now, technically, I only have one term here, so there's no factoring to do, but I'm just going to add this step just so as a reminder for the future. So if you have dy over dx in multiple terms, take it out from all of them. So collect all the dy over dx's in front, and then ask yourself, what would happen if I remove the dy over dx from this term? What would be left? Put it inside the parentheses. And do that for the next term, and the next term, and the next term until you're done. In my case, I only have one term, so I'm basically finished now, and it still all equals to negative 2x. And finally, step number 4 is going to be to solve for the dy over dx, meaning get this dy over dx all alone. And the way you get it all alone is you look, it says dy over dx is being multiplied by 2y. So to get it all alone, I need to divide both sides of the equation by the 2y. So I already have negative 2x, and I need to divide it by 2y. So in other terms, what we are saying is that the dy over dx, the derivative that we're searching for, is negative x all divided by y. And that's because I can divide by 2 and divide by 2. And when I divide by 2, I just get negative x over y. So this is the derivative of the expression or the equation of the circle that we were given. So I hope that made sense, and that's only one part of the problem. Now remember, after finding the dy over dx, they said to use it to determine the equations of the lines, and there are technically two lines. One line for the point 3,4 and another line for the point negative 3,4. And when I'm done, they want me to draw those tangent lines. So let's pause for a second and think about the point 3, 4. We need the tangent line at the location. So the tangent line is going to be given by the equation y minus y1 equals to m times x minus x1. So it's the same point slope formula that we've always used in every previous section to find the equation of any line. We said if you hear the words find, equation, and line in the same sentence, this is the formula that you need to start with, and you got to ask yourself, are they giving me an x1? Are they giving me a y1? Are they giving me a slope? If they are, then great. If not, then you have to find the numbers yourself. In my problem, they are giving me x1. It's actually 3. And they were being super generous. They gave me the y1 actually, which is 4. The only thing I'm missing is m. M is missing, and remember, m is the slope of the tangent line. And the big idea of calculus is that m is really the derivative with the numbers plugged in. So in this case, the numbers 3, 4 plugged in. So remember this new notation? I introduced it in a recent video. It basically means m, the slope of the tangent line that you want, is the derivative. That's what the dy over dx is. And I put a little slash over here like a vertical line. And that notation just means that I'm about to plug in the numbers 3, 4 into this derivative. That's what this notation means. So remember, my derivative is negative x over y, but I'm going to replace x with 3 and y with 4 to see what the answer is going to be. So x is going to be 3 and y is 4. And I don't really have to do anything here. It doesn't reduce to lowest terms or anything. So that's it. The slope of the line is negative 3/4. So that's the number that needs to go into the m. So therefore, the equation of the line becomes y minus 4 equals to negative 3/4 x minus x1, but x1 is really the number 3. And so that's it. We found the equation of the line. Now, it's helpful to rewrite it a little bit. differently. It's helpful to have the y all by itself on one side. So I'm going to take a little bit of time here to first distribute the 3/4 to the x, then distribute the negative 3/4 to the negative 3. That gives me positive 9/4. And I'm going to move this negative 4 to the opposite side by adding it to both sides of the equation. And this is almost the end. I'm just going to do one more thing here, which is write down the negative 3/4 x and add these two fractions. We can add them with a calculator or we can add them by hand. The bottom line is when you add them, it's going to be 25/4. That's because 9/4 plus 4, I can think of the 4 as being over 1. Then I'll have to multiply by 4 on both the numerator and the denominator to get the common denominator. And then I'll have 9 plus 16, but 9 plus 16 is really 25. And so this is the equation of the line at the point 3, 4. So one of the two lines has been found. Now we need to find the equation of the second line on the second point. So remember, the second point is the point -3, 4. And we want the tangent line, which again, to find the tangent line, I need to use the same point slope formula, y minus y1 equals m times x minus x1. It's the same kind of process as before, except the x this time is going to be -3. The y is still going to be 4, and m is again missing. Remember, this is a different line, so it's a different slope. And how do I find m? I take the derivative that I just found, and I plug in it the numbers -3 and 4. That's what this notation means. Remember, the derivative was negative x over y, right? Remember, it's way up here in the first box that we found. But instead of x, you're going to write down -3. So I'm going to put -3. It's a double negative. And it's all divided by the y. But instead of y, I'm going to write down the value 4, because that's the y coordinate of the point that I am interested in finding the equation at. And by the way, -3 is going to be 3 divided by 4. There's nothing to do there, so this is the end. Just like the previous one, the answer was -3/4. Here, the answer is 3/4, and that represents the slope of the line that we are interested in finding. So my equation becomes y minus y1 equals to m times x minus x1, but the y1 is actually 4, the m is 3/4, and the x1 is really -3. So now that we have all these numbers, we will just need to rewrite the equation slightly so that it looks slightly better and so that it'll be consistent with the previous one. So first, I'll distribute the 3/4 again, and I'll have 3/4 x. I'll distribute it again. This is a double negative, which means it's going to be positive. And 3 times 3 is going to be 9, so this is positive 9/4. And I'm going to move this -4 to the other side, and that makes it positive 4. So the equation is going to be 3/4 x plus, again, 9/4 plus 4. You can put it in a calculator or do it by hand, whatever works for you. Anyway, it's going to be 25/4. And the equation is almost the same as the previous one. The only difference is one of them has a negative slope, the other one has a positive slope. So let's go back to the picture that we have on the previous page. So we basically have decided that both equations are virtually the same. And for the first line, the line kind of looks like, -3/4 x plus 25/4. So the line kind of looks like this. And this line has the equation -3/4 x plus 25/4. It's got a negative slope. That means it should be pointing down as we walk on it from the left to the right. It should be pointing down. That's the indication for that is the negative slope. And on the other hand, the other line has pretty much almost the same equation, but it's got a positive slope instead of a negative slope. So this is what that line looks like. And as I walk on it from left to right, the line is going up. This is the line with the equation 3/4 x plus 25 over 4. As I walk on it from left to right, I'm going uphill. Okay, so let's see what else they want us to find. So example number 2, part 2 is done, and now part 3. It says, from your graph, determine where the curve has a horizontal tangent line and where the curve has vertical tangent lines. And they want me to also verify the slopes of these lines using the expression for dy over dx. Remember, the expression for dy over dx, we found it ourselves. They did not give me this. It was negative x over y. And they want me to find the places where the curve or the circle has horizontal tangent lines and where it has vertical tangent lines. So let's go back to the picture real quick and see what they are talking about. So this is the circle, and there's a place here on top where the horizontal line would be, where the tangent line would be horizontal, and there's another spot here on the bottom where the tangent line would be horizontal. And these are probably these locations, 0, 5, and 0, negative 5. At those locations, the tangent line looks like it's going to be a horizontal line. And there's also two locations, one on the left and one on the right, where the tangent line, if I were to draw it, would be vertical. And these are the locations that probably are 0 or 5, 0 and negative 5, 0. These are probably the numbers there. They want me to find them analytically, meaning use the expression that I just created to find what these points are called. And we can see from the graph there's going to be a lot of 5s, but they want me to confirm this using the derivative. And remember, the derivative is just negative x over y. So, okay, from the graph, I can see that the curve has some horizontal tangent lines and some vertical tangent lines. So let's start with horizontal tangent lines. I'm going to write HCl for horizontal tangent lines. So on my circle, these places were the top of the circle and the bottom of the circle. So I think the answers are supposed to be 0, 5, and 0, negative 5. These are the locations at the top and bottom of the circle. They are both on the y-axis, and so the x-coordinate is going to be 0, and the radius is 5, so I expect the answer to be 5 and negative 5 for the y-coordinates. So this is my guess at this point in time, but they want me to confirm this using this equation. Okay, so how do I confirm this using the equation? How can I be sure? Remember, we can't rely on graphs because sometimes the graphs lie to us. Maybe we drew the circle wrong or something else. Who knows? So to confirm that my intuition and my guess is correct, I'm going to say, okay, to have a horizontal tangent line, the slope needs to be 0. For horizontal tangent lines, the slope of their line is going to be 0. So in other terms, what I'm saying is I need to solve the equation dy over dx equal to 0. So in other terms, I'm saying I want the equation negative x over y to be 0. Remember, dy over dx is the derivative, and the derivative was equal to negative x over y. Now, this is a circle, and the circle is equal to 0, so there's different ways to think about it, but the bottom line is the numerator has to be 0 for the fraction to give me a 0 at the end. Another way to think about it is I can think like negative x over y equal to 0, and there's always an invisible one there. And I could just cross multiply the numbers. I get negative x equal to 0, which means x is going to be 0, because 0 times y is 0, and 1 times negative x is just x. So regardless of how you think of it, you should know that if a fraction equals 0, that means the numerator must have been 0. So that confirms my first intuition, which is that the x-coordinate of the point should always be 0. Now, how can I get the y-coordinates of these points? I need to remember that the equation we began the problem with is this equation x squared plus y squared equals to 25. It's the equation of the circle with radius 5 centered at the origin. So replacing x with 0 in this equation should help me find what the y is going to be. So if I replace x with 0, then I get 0 squared plus y squared equals to 25. So replacing x with 0 gives me this equation. And remember, 0 squared is just 0, so this means that y squared has to be 25. And the numbers I squared to get 25 are either plus 5 or minus 5. And this result confirms our intuition and what we saw on the graph earlier. We thought that the place where the curve will have a horizontal tangent line would be at the top of the circle and at the bottom of the circle. And we are saying now that yes, this is true, and that this point here is called 0, 5, and that this point down here is called 0, negative 5. So that's half the problem. The other half tells us to confirm the vertical tangent lines, and we think that they are going to be at 5, 0 and negative 5, 0. So let's go ahead and confirm that again using the same kind of math that we did here. So for horizontal tangent lines, we're finished. Now let's look at vertical tangent lines. So for vertical tangent lines, we think the numbers are supposed to be 5, 0 and negative 5, 0. So that's what we saw on the graph. And remember, this is the place where the circle ended on the left and on the right. Those places we will have a vertical tangent line. So we just need to confirm this result by doing a little bit of math like what we did previously here. So first, again, I need to rely on the derivative. Remember, we always use the derivative to solve these types of problems. And again, my derivative, I just want you to recall that the derivative in this problem is dy over dx equals to negative x over y. Now, I am dealing with vertical tangent lines, and so vertical tangent lines have the slope which is undefined. They are vertical, but there's no slope to speak of. So that means for this expression to be undefined, I need the denominator to be equal to 0. Because if the denominator is equal to 0, we won't be able to divide by 0, and the whole expression becomes undefined. So in other terms, we're saying make the y equal to 0. If the y is equal to 0, negative x divided by 0 will become undefined, and that's it. You're done, basically. Because that confirms that the location that we found is correct. The second point in the coordinates is, or the second coordinate in the points is 0. But how do we find the x? Well, we go back to the original equation, which was x squared plus y squared equals 25. And so now we know that y is equal to 0. So that means x squared plus 0 squared has to be equal to 25. So the y is getting replaced with 0. And so x squared has to be 25, which means that x has to be either plus 5 or negative 5. Those are the numbers you square to get 25 at the end. And these numbers are the same numbers that we suspected when we looked at the graph when we drew the circle. So going back to the picture over here on this page, we are now confirming that there's a vertical tangent line here and another vertical tangent line here. And those locations, by the way, are called 0, negative 5, and 5, 0. And that will be basically the end of this problem. So we did a lot with this problem. It's one of the important problems in this class. It basically summarizes everything we've done so far this whole semester. So it's a really good problem to pay attention to, and maybe rewatch the video if you didn't catch part of it, or see me in office hours and let us discuss what you're missing. Okay, in example number 4, we have a straightforward problem. It says find the dy over dx, meaning find the derivative, and we're given some kind of equation. And remember, this problem has some x's and y's mixed up together. It's probably very difficult or even impossible to isolate the letter y, so you'll need implicit differentiation. Then they want you to find the answer and use it to find the equation of a tangent line at some random point called 1, negative 1. So for now, let's ignore that part for a second. Let's focus on the first part of the problem, which is finding the derivative. So in step number 1, as usual, we take what was given to us and we announce to the world that we're about to do some derivatives, and we're putting d over dx because we're seeing that they want dy over dx. So the number on the, or the letter on the bottom is x. And so that's why I'm writing d over dx. Remember, the dy gets created later on when we differentiate any letters of y. In this case, there's going to be 2 of them. So that's step number 1. And so that now that you've announced to the world that your intention are to differentiate, go ahead and actually find the derivatives. So we begin with the 4xy cubed. Now remember, between the 4, the x, and the y cubed, there's a multiplication sign. So actually, to differentiate this part, you will need a product rule. And so let's write down the parts of it on the side. What is the f and what is the g? The f is 4x, the g is y cubed. And we need f prime, we need g prime as well. And the f prime and the g prime are the derivatives of 4x, which is just 4. And the derivative of y cubed, remember, with respect to x. So derivative of y cubed with respect to x is going to be 3y squared, and then dy over dx, the derivative of the inside. And the rule tells me to multiply the corners and add along the way in the middle. Okay, so the derivative of 4xy cubed will be 4y cubed plus, I'm supposed to multiply these 2 corners with each other. Okay, 4 times 3 is going to be 12, xy squared, and dy over dx. Now we get to the plus sign. I'll write that next. And what I'm about to differentiate next is just the 5x. And the derivative of 5x with respect to the letter x, this is the usual, it's just 5. Then I get another negative sign, so I'll put that next. And now what I want to find is the derivative of 2y. Now remember, 2 is just a constant, so it goes for the right. And what about the derivative of y? Well, the derivative of y is 1, but the letter y does not match with the letter on the denominator. So the variables are not the same. That's why I need to write dy over dx also over here. So you know what? Let me put it in a different color so we can kind of identify that this 2y is 2, 1 dy over dx. By the way, 2 times 1 is 2, so let's just write 2 instead and just save a little bit of time. And finally, I want the derivative of 3 with respect to x. The 3 is just a random number, doesn't have any variables, so its derivative is just 0. So this is all step number 1 of the process. And step number 2 is to try to isolate the terms that have the dy over dx. So we want to put this term and this term on one side of the equation, and everything else has to move to the other side. So let's begin by removing the 4y cubed. To remove it, I need to subtract both sides by 4y cubed. To remove the 5 to the other side, I need to subtract both sides by 5. So now this guy is gone, this guy is gone, and what's left is the 12xy squared with the dy over dx, along with the negative 2 dy over dx. The terms that have the dy over dx will remain together on one side of the equation. Okay, now that we have isolated all the terms that have dy over dx on one side all by themselves, and we've put everything else on the other side, now our job is to factor this expression and get the dy over dx away from everything else. So we're going to take the dy over dx and factor it out. And when I factor it out, what's left is going to be 12xy squared and just negative 2. So basically, I'm grabbing the dy over dx and I'm erasing it and putting it outside. And then what's left over goes inside the parentheses. And then I repeat the same thing on the other guy. So first I grab the dy over dx and I put it on the outside, and whatever's left goes on the inside of the parentheses. Simultaneously, the other side just stays the same. We don't have to do anything there. Negative 4y cubed minus 5 is going to be the same forever. And the last thing we're going to do is write down step number 4, where we will finally get the dy over dx to be alone. by dividing by the term, by the parentheses. So I need to get rid of the parentheses, and I see that it's being multiplied by the dy over dx, so I do the opposite multiplication, which is division. So my numerator is going to be negative 4y cubed minus 5, and I'm going to divide by 12xy squared minus 2. So this is the process of finding the derivative dy over dx, and I need to do all this because the next part of the problem says we want you to find the equation of a line, or a tangent line rather. But regardless, I need equation of tangent line and at the point 1 comma negative 1. So remember, the process is always the same. The start is always y minus y1 equals to m times x minus x1. This is the point slope formula. We always start here and we ask ourselves, what's given to us? Do we know an x1? The answer is yes. The other thing is, do we know y1? And the answer is yes. And finally, do we know m, the slope? And the answer is not really, not 100%, but we can use this to find m. To find m, we just need to know the derivative, and we plug the numbers 1 and negative 1 into it, and that gives us the slope. So in this problem, the slope is going to be the dy over dx with the numbers 1 and negative 1 plugged in. So my equation is negative 4y cubed minus 5 divided by 12 x y squared minus 2. But instead of the y's, I'm going to be putting negative 1. So every time you see a y, you're going to put negative 1. And instead of the x, you're going to be putting 1. So my x is there. I'm going to erase it. And instead of the x, I'm going to write down 1. And that's because the point that's given to me has 1 for the x and negative 1 for the y. And you can spend a little bit of time here doing this by hand or using the calculator. It's up to you. It doesn't matter. The bottom line is the numerator should have negative 4 times negative 1 minus 5, because negative 1 cubed is negative 1. And this multiplies to be 4. 4 minus 5 is going to be just simply negative 1. That's the numerator. The denominator has 12 times 1, which is 12. Negative 1 squared is going to be 1. And 12 times 1 is still going to be 12. And then minus 2. And 12 minus 2 is really 10. So the slope that we're looking for is negative 1/10. This is the slope that we are interested in finding. Let me make all of this smaller so that we can fit the rest of the problem. And the last thing we want to do is put all the numbers back into the equation. So this equation here becomes y minus the y1, that's a negative 1. It's equal to m, which is negative 1/10, and x minus x1, which is the value 1. So this is the x1, this is the y1, and notice how there's a double negative there because the formula comes with a minus sign already, and my y1 is negative, and finally the slope itself is also negative 1/10. So y plus 1 equals negative 1/10 x plus 1/10. We are going to move the 1 across by subtracting 1 from both sides, and when we do that we get negative 1/10 x and minus 9/10. Okay, that's because 1/10 minus 1, that's the same thing as 10 over 10, is going to give me the same denominator, 10. 1 minus 10 is going to be negative 9. That's how I'm getting this fraction. Or you can use your calculator to find it, no big deal. So the solution is that thing in the final box, negative 1/10 x minus 9/10 equal to y. That is the equation of the tangent line. Lastly, in this section, we have to work on an application problem. This is a business application that says the number of calculators produced when X dollars is spent on labor and Y dollars is spent on capital invested by a manufacturer can be modeled by the equation. And the equation is written in the middle of the page, 40 times X to the power of 3/4 times Y to the power of 1/4 equals to 2,160. They want me to find dy over dx, meaning the derivative, and then evaluate the derivative at the point 81/16. So there's two parts of this problem. First, we need to find the derivative. Then we need to put some numbers in it and get the slope of the line. Now, let's begin with the equation, which is 40x to the power of 3/4 and y to the power of 1/4 equals to 2,160. So the first thing we're going to do in this problem is announce to the world what we're about to do, then find the derivative, and so on and so forth. It's the usual same steps, but I'm going to try to make the problem a little bit simpler by first noticing that I can divide by 40 on both sides of the equation. And if I divide by 40, the numbers will become a little bit simpler, and I don't have to worry about the 40 and the 2,160. Those are kind of big. I don't want to keep writing them over and over. So let's just start by doing that step first. So I'm going to divide by 40, and whatever you do on one side, do the same on the other side. And the purpose of this step is just to make the numbers a little bit more manageable. And we know that when we divide by 40, this is going to be 1 over 1, which we don't have to write down anymore. So we have now x to the power of 3/4, y to the power of 1/4 equal to whatever 2160 divided by 40 is, and the answer should be 54. So this makes the numbers a little bit more manageable, and it's going to help me in the long term. Now, if you didn't do that, it's not going to be the end of the world. You're just going to deal with some numbers in your mix, but it's not a huge issue. It's not a big deal. The other thing I want to point out here is that x to the 3/4, that's the same thing as 4th root of x cubed. And also y to the 1/4 is the same thing as the 4th root of y to the power of 1. So if you recognize this, we can actually rewrite the problem with the 4th root of x cubed y1 equals to 54. This may be a little bit better because we can avoid having the radical in the problem, and if we don't have a radical in the problem, we will make the differentiation process easier later on. So by doing this, I can now take this side and raise it to the power of 4, and whatever you do on one side, you can do the same thing on the other side. This will help us remove the radical from both sides of the equation. Well, at very least, remove it from the left side. So x cubed y is going to be 54 to the power of 4. I don't know what that number is, and I don't really care, honestly, because in a moment, I'm about to say to the world, I want the derivative with respect to x of whatever's on the left, and then do the same thing on the right side. So remember, the point of doing all of these steps, the point of doing all this algebra steps, is to make the problem simpler. By doing these steps, I can avoid some really nasty product rules and power rules and so on and so forth later on. And if you don't do them, it's not wrong, but you'll just have to deal with a little bit more obscure or harder numbers. Now, let's start with the derivative of the 54 to the power of 4. This is just a constant. Its derivative is going to be 0. So that's why I didn't care to find out what 54 times 54 times 54 times 54 is, really. Like, it doesn't really matter to me because its derivative will be 0 anyway. Now, on the other hand, though, I've got x cubed times y. So this is a product, and I'm finding the derivative of the product, so I need to do a product rule there. And remember, the product needs f and g, and f is the first term, which is x cubed, and g is the second term, which is y. So what's the derivative of f? What's the derivative of g? Derivative of x cubed is 3x squared. And I'm differentiating with respect to x, so I don't need to put anything new here. I don't need to add anything to this answer. However, the derivative of y will be 1, but I'm differentiating with respect to x. So I need to add the extra dy over dx to the bottom. And now the rule tells me multiply f prime g and then g prime f and add in the mix. So that means multiply these corners, we get 3x squared y. Then the rule says add. That's what is written right there in the middle. So I'm adding, what am I adding? The product of these two corners. And remember, x cubed times 1 is just x cubed with the dy over dx going for the right. So as you can see, my derivative is now easy. And if I had not done all this algebra at the beginning, right now I would have to be doing the product rule with the really ugly powers x to the 1/3 or 3/4 and y to the 1/4. And the negative powers are going to be a problem and all that mess. This is just way better. It makes it way easier. Now, remember, our goal is to get the dy over dx by itself. So let's try to do that next. So I'm going to isolate it by itself by first subtracting the 3x squared y. And finally, I'm going to remove the x cubed from this left side by dividing. Since it's being multiplied by the dy over dx, we just divide both sides by x cubed, and that gives us the final answer. And by the way, there's an x squared and x cubed on the numerator and denominator. We can reduce it all to lowest terms by just dividing the terms out. So we can get rid of a couple of x's on the numerator and a couple of them on the denominator, and my final answer should be negative 3y over x. This is the derivative that we wanted. So that is the end of the first part of the problem, which said find the dy over dx. But not only that, they want me to evaluate the derivative at the point 81 over 16. So, 81 comma 16. So at the point where the x coordinate is 81 and the y coordinate is 16, what is my derivative? The dy over dx evaluated at the point 81, 16 will be negative 3 times the y, which is 16 for me, divided by the x, which is 81. So remember, the x goes on the denominator because that's where x is found, and the 16 is the y. It goes on the numerator because that's where the y used to be. And so that's it. The dy over dx that we're searching for is whatever this guy is. You can plug it in your calculator to get the answer or do it by hand. It's up to you. I can notice that the 3 and the 81 can be divided by 3. So if I divide them both by 3, I end up with negative 16 over 27, and that's my final answer.